So welcome to this second part of the training webinar. So today we will have two parts in the session. Let me start with the first part, that is the implementation of the decision trees with Python and Colab. So let me share my screen. Okay. So I send you a link. Ramaj send you an email in which you have a shared notebook with Python that is directly linked to Colab. So if you click on this link, you will obtain, once you are logged in on Colab, you will obtain this page on which you have, okay, here the notebook Python, so in which you have some code and text, okay? And then on the left, you have some commands that we'll use in a few minutes. So if you want to run the code with me or to change something, please, as a first stage, please save your Python notebook as a copy of this link, because otherwise we will work together on the same file and it will be difficult because if you change something, it will change on my screen, it will change on the notebook of all your colleagues, okay, of all the participants. So please first save a copy in your drive. So here, if I click here, it is in French, but enregistrer une copie dans Drive. So save a copy in Drive, and then here you will obtain, after a few seconds, a copy of the notebooks that I send you. Okay, so now you can work on your own copy of this notebook, and then you can make all the changes that you want without changing the code and the notebook of your colleagues. Okay, so the first, as I mentioned in the last week, a notebook Python allows you to introduce some text and some code. So here I can add some code, or okay, and okay, and here I can also add some text with a markdown, whatever. Okay, and I can add some text. Okay. So in my notebook, I have a set of instructions, a list of instructions that we will run directly on the Google Cloud without installing Python on my own computer. This is the main advantage of Colab. The second advantage of Colab is that, okay, it allows to collaborate with your colleagues on the same code and to make some change and to make some versioning of your code, etc. There is many advantages, but I don't have time to detail the advantage of Colab. Okay, but the main advantage for me at this stage is that I don't have to install Python. I don't to take care about the version of Python, the version of packages, etc., etc. So I can use the version of Python that is available on Colab. So once you have saved a copy of this Python notebooks, the second stage, the second step, consists in uploading some file. So first, I send you two files, so scoring data XLS, so an Excel file, and function .py file, that is a Python code. So I need now to upload this file. So for that, I click here on the left of my screen on this symbol. And then here I have a button that allows to import a file in my storage on my drive. Okay. So here I have to upload two files. Or first, functions.py and scoring data.xls. Okay, so let me start with function.py, so code for function, and then you have a warning, but whatever. And here now you see on your left that this file is available in my working space. I will do the same. So I upload the file, the data file, the scoring data. And here, okay, I have a message about the upload. If it takes too long time, you can redo the import. Okay, so for instance, if I redo the import here, up, now scoring data xlx6 file appears on my working space, and then I have my data and an additional file in which there are some codes, and I can run my notebook Python just to introduce you the, the decision trees. Okay, is there any question? No? Great. So, the first block of instructions is this block in my, I will, okay, increase the size of my screen. Okay, so in this block, there is a list of import instructions, and this import instructions allow you to import some packages. So Panda, it is a package, is a library in which you have many functions to manipulate the data. NumPy is to make some calculus. But what is important for you, for instance, is that I will use scikit-learn. Scikit-learn is a well-known library for machine learning in Python, in which I will find many functions to train or to evaluate machine learning models. Okay, so here, let me go back here. From scikit-learn, I will import this function, which is called decision tree classifier. I guess that you understand what is the goal of this function. I will also import grid search, CV, cross-validation. I guess that now you understand what is the goal of this function, etc., etc. So I have to import some specific function from scikit-learn using these instructions. I will also import a package from a function XGB from library XGBoost. So XGBoost, it is a library from DMLC that is related to the gradient boosting models in general and XGBoost in particular. And from this library, I have to import a particular function. Okay, whatever here, I import all the functions from XGBoost, etc., etc. So how to run this block of instruction, I just have to click here on the left on this sample, and then it takes 0 seconds to run this part of the code. Sorry, I didn't translate, but okay. Okay, it's really easy. Sorry to understand. I forgot to translate the text. Okay, but here you have a second instruction in which I have a variable, and the name of this variable is seed, and I fixed a value, whatever. I can change the value. Okay, for instance, okay, it is an integer, okay, value, but okay, you can change the value and choose whatever. And then by executing this instruction, I affect value of 42 to the variable seed. This variable will be used during all my code, within all the instruction in my code, to fix the seed of the random generators. For many of the codes that we will, or functions that we will use, there will some random draws. For instance, when I built my training sample and a test sample, I have to make a draw, a random draw. And then the problem, some individuals are put in the training data set, other in the test set. This is the same for the cross-validation, whatever. And the problem with that is the fact that if I want to reproduce the result next week, if I want to find exactly the same value, the same estimate, the same prediction, etc., I have to redo exactly the same draws, okay? So in order to control the reproducibility, in order to control the draws and to redo in the future the same draws that I have done today, then I will fix the seed of my algorithm, and I will fix it with a value that I have here. Okay. Okay. The third block of instruction is just to import the data set. So for that, I will use the Panda library. Here you have import Panda as PD. PD is a kind of nickname for all the functions that belong to the library Panda, okay? So when I call a function from Panda, I have to write, I should write Panda point the name of the function. In order to reduce the, uh, the size of the instruction, rather than to write pandas point the name of the function, I will write PD point the name of the function. So PD is a kind of short title of short name for the library Panda. Okay. So from the library Panda, I will use the function read Excel. Okay. Okay. Panda read Excel. So we are here in the Panda library. There is a function that is called Panda read Excel, but here, due to my change of name, it is PD point read Excel. And then I have many options to import an Excel file in Python. So here, the syntax is very simple. PD read underscore Excel, the name of your Excel files that you have import here. So it's coring data underscore data point xlx6. The name of the sheet of the sheet in which you have the data. So let me illustrate. Up. Let me go back to, sorry, I have a problem. No, it's not a good up code. Okay. Do you see the yes, you see the Excel file. So this is a scoring data Excel file. So in the first sheet here, the name is variables, and you have the dictionary of the variable. So this is a credit scoring application. And so we have a default indicator. This is a target variable that takes the value 1 or 0 if there is a default. Okay, and then we have a set of explanatory variables that could explain the default, and it's a credit scoring. Huh? Okay, so this is the job tenure, the age of the borrower, the car price, the funding amount, the monthly payments. The variables, it is a down payment, which is a binary variable that indicates if the down payment exceeds a given value of the car value, a given percentage of the car value, the loan duration in months, a credit event that indicates if there are a default in the past, the marital status and the homeowner status. Okay, so this you have the dictionary, and for each variable, you say that, okay, this is a categorical or continuous variable, whatever. And then in the sheet data, you have the data. So for instance, for the first individual, there is no default. The job tenure was 34, the age was 55, the car price, etc., etc. Okay, so I have just to indicate the name of the sheet that includes the data. So here, sheet name is equal to data. And then I can also put with the option index col the number of the column of the file in which I have the index of my individuals. Okay, so let me go back to my Excel file. Okay, in the first column, I have the index of the individuals. Okay, this is the first individual, second individual, etc., etc. So I have to, okay, to indicate to Python that, okay, in my Excel file, the data start at this column, okay, and for that I have to say, okay, my index is the first column. But with data, with Python, there is a subtlety, because when you have a matrix, the first column is indexed by 0. The first line is indexed by 0. So let me illustrate here. This is the first line. And when I want to refer to this line, I say, okay, the line 0. This is the first column here. And when I want to refer to the first column, I have to say, this is the column 0. So just to say the index of my individuals are included in the first column, I have to write index underscore col is equal to 0. Is there any question? No? So then you have just a control, and to make a control, I recommend to display the 10 first lines of your database. So data head, in parentheses, a number, for instance, 5, it just allow you to display the 5 first lines of your data set. Okay, so if I run this block of instruction, so this is a control. Okay, for the first individual, I can check that I have the same data than in my Excel file, and there is no problem of import. The second individual, there is a default. The job tenure was only 5 months. The age was 29. The price of the car was 13,000 of euros, etc., etc., etc. Is there any question? No? Great. So now we explore the data sets with Python before to make machine learning. Okay. And just, for instance, with this part of the of instruction, we will use. Just if you remember well, I store the data in an object issued from the function readExcel that is called data. Okay. With this data frame, I can make now many operations, and most of them will use the same syntax. This syntax is data point something. So for instance, data point shape in 0 will indicate the number of lines. Data shape 1 indicates the number of columns. So here I have an instruction that say, okay, print these databases as into brackets number of observation and into brackets number of variables /n, and /n means that these brackets will include the value of data shape 0 and data shape 1. Okay, so /n is just to make a space. Okay, and into brackets. So here you will use this value and compute this value, and it will be replaced here. So okay, the second instruction. So if I run this block, okay, this database is as 7,440 observation and 11 variables. Okay, 11 features. Okay. Then I want to list the name of the variables in my data set. So the name that I can find here. Okay. And so for that, I have a loop for var in data columns. So data columns are the columns of my data set. And then I have a loop on the index if you want. Okay, this kind of an index on the column of my data set. And then I print var. This is simply the name of the variable in my data column. Okay. And so you have here default, job tenure, age, car price, etc., etc. And this is just a warning. Is there any question? Okay, great. Another instruction that is that could be really interesting for you is data describe. Data, the name of my data set, point describe. This is a really easy way to produce a descriptive statistic for all your variables. So data point describe with parentheses allows you to produce descriptive statistic for the dependent variable, for all the variables in the data set, so the dependent and the feature. Okay, so you have the count, the mean, the standard deviation, the minimum, the quantiles, etc., the maximum. Okay. I have no particular, but just, okay, we observe that there is a default rate of 20% in the data set. Here, I indicate, but it is not necessary, but just for some graphical representation, I have to distinguish and to declare what are the quantitative variables and what are the qualitative, the discrete variables. Okay, so what are the quantitative variables? Here I have the job tenure, age, car price, funding amount, loan duration, monthly payment. Remind that, okay, down payment, credit event, married, homeowner, and default are binary variables. So I declare that I have 5 discrete variables: default, down payment, credit event, etc. Okay. So in this variable, qualitative variable, I have only the names of the variables that are discrete or quantitative in this vector. There is here an instruction to make a visualization of your data. This is this, okay? And data, so this is not a reserved name here, equal the name of your data set, of your data framework, okay? So here, data is equal to data because, okay, on the left, you have the reserved name, and on the right, you have the name of my data set. And then once I have launched this instruction, then I can produce some graphs, okay? Remark that now I have stored the visualization of my data in this object, which is called graph. And then I use this object graph to produce some graph, and for instance, the distribution of my variables. So for people who know what it is, so here you have, depending if the variable is discrete or continuous, var distribution. So var distribution, okay. Well, I will find you the instruction later. First. I think that it is, sorry, this is a function that is included in my function pi. Okay, sorry. So this is a function that I've defined in this function pi, okay? And just, this is a function that produce automatically the graphs, okay? So, of the distribution. So for the binary variable, I have an histogram. And for the continuous variable, I have what we call a kernel density estimate of the density, kernel estimate of the density. Okay, so this is an estimate of the density of the variable job tenure. Okay, so what we observe, for instance, we have two types of people. We have some people around 25 years, and then, sorry, we have people around 50 years, etc., etc. So I have many information. If I want to open this graph, okay, in a new in a new in a new file, not a new file, but a new outcome. I remember. I don't remember.
Tab.
Tab. Yes, thank you. In a new tab, so okay, you can run, and then you can also save the image, all the images produced by Python with on JPEG and whatever, okay? In PNG or JPEG, whatever. So let me, okay, go back here. So, I can, by changing, this is a function that I made in my function .py, okay? So if by changing the name of the variables that I want, for which I want to reproduce the distribution, and for instance, here, I limit the set of variables to two quantitative variables, age and funding moment, and one qualitative variable that is married, okay? And then I graph, sorry. I graph, donc I take the object graph, I represent the distribution of the variable for these quantitative variables and for these qualitative variables. And just this is some option for the size of the figure and the label size, the title size, and the font size. And then I focus on this three distribution. Okay. What is more interesting for a preliminary explanatory variable is to observe if there is a change of the distribution of the feature with the default. Okay, just to explore if there is, for instance, some variables that are a priori related to the default. Okay, so in the function pi, I produce a function that is defined by var distribution by default. So if I run the code, this is exactly the same figure as before. So I have the histogram for the binary variables, and I have a kernel density, kernel estimate of the density for the continuous variable. But now, for each variable, we have the density or the histogram of the variable obtained with for people who have default and for other people. Okay, and so for instance, what is the outcome here? We observe that, for instance, homeowner has a different distribution for people for credit in default and for credit in non-default. So maybe there is a relationship between the two variables. This is also the same for married. But on the contrary, for instance, for down payment, the difference is not so clear. For monthly payments, this is not really clear that there is a difference. For the car price, it seems that the car price has no clear relationship with the default. And for age, maybe there is a link between age variable and the default. I can do exactly the same exercise for a subset of the quantitative variable and the qualitative variable. And this is exactly the same syntax. So for these variables, quantitative and qualitative, I can produce a distribution var, a graph of the distribution of the variables, depending if there is a default or not. Okay, so I don't have the time to recommend you a pipeline of pre-treatment of the variable. Maybe I have to check if there is some correlation between my variable. I have to check if there is missing variable. I have to check. I have to discretize some variables or to the continuous variable or to make some regroupment of class for the discrete variable, etc. But this should be the object of a webinar in itself. But now we have to explore the application on this data set of a decision tree. Okay. Is there any question? No. Okay. So first, remember that data is the name of the data.
Question.
Yes.
Okay. I was asking about the functions .py. Will we find like other format for this for different economic analysis functions, or we should build it from scratch ourselves?
Well, you should. Sorry, I didn't hear the end.
Yeah, we should build it from scratch whenever we are doing any kind of analysis. Are there any like pre-prepared function .py like this one you prepared, or usually each one who is working on data should work on his or her own function .py or something like this?
I'm not sure to well understand. Okay. In general, you have to prepare your data.
Mm-hmm.
Okay. And okay, there is a lot of literature about the way you have to prepare your data before to use machine learning models, okay?
Mhm.
For this webinar, I decided to not focus on the preparation of the data itself, okay?
Yeah.
But on the algorithm, because, okay, it is more complicated to understand the algorithm, for instance, of a random forest
Yes.
than to understand how to prepare the data, okay? To prepare your data, there are many pipelines, so a kind of of, um, of a list of treatment that you
Mhm.
have to apply to your data set depending on the algorithms that you want to use. Okay, for instance, in general, it is recommended to discretize the continuous variable, but for the decision tree, it is not necessary because the decision tree will discretize the continuous variable. Okay. For instance, it is recommended to standardize the variables. Okay,
Mhm.
so divided by the standard deviation, or to normalize to compute the difference between the minimum and the maximum, etc. But
Mhm.
it is also the same for instance, for a decision tree. It is not necessary, okay, because there is no problem with this if you have non-standardized series for this algorithm. This is not the case, for instance, for k-means. So depending on the type of algorithms that you have to implement, you have to, or not, it is recommended or not to do some pre-treatments. Let me also detail the question of missing variables. If I have some missing variables, this is not a problem for a decision tree, for instance, because, okay, the decision tree can say, okay, if there is no observation for the age, then, okay, I will put all the individuals with no information about their age in a subgroup of the population, okay?
Mhm.
For other algorithm, it is not possible to use missing data or to let missing data. So you have to use missing imputation method, okay? Let me also elaborate about the fact that, okay, for instance, here, the target variable, we observe that there is 20% of default and 80% of the observation for which there is no default. So my data are not disequilibrated, okay, are not unbalanced. Sometimes we have very, very few observation of the y equal to 1 variable, okay? For instance, very few default, less than 1% and 90% of zeros. And for some algorithm, in particular for the decision tree, random forest, etc., it could have some consequences on the learning process. So I have to reduce the number of zero or to increase the number of one by some methods before to start my to launch my model. Okay, so just to say that is why you will find. I think that if you are in mind, for instance, to run a random forest model, then on the web, you will find a list of the pre-treatments on your data that are recommended in this case, okay?
Mhm.
And then it is really easy to get or to copy the instruction to do this type of pre-treatment, for instance, to impute some missing value or not, or to standardize or not, or to discretize or not, or to transform the discrete variable into binary variable with a one-hot encoding, for instance, approach or any other approach. But okay, there is a list, and it is really easy for standard algorithms at random forest, decision tree, XGBoost to find a list of these pre-treatments. Okay.
Thank you so much.
Okay, so remember that in data I stored my data set. So here I use the function drop just to remove one column that corresponds to my target variable, which is a default variable. Okay, so this is just an instruction to remove a column in my data set. So I take my data and I remove the variable default. On the contrary, here for y, I use my data set, and here this instruction allows me to select the column or the variable for which the name is equal to default. So in Y, I have only one variable that corresponds to my default. This is clear? Okay, this is the first decision tree. Train a decision tree, but for others, this is the first training of a decision tree, and this is very disappointing because, okay, I have no result. Okay, so first, let me describe the syntax of a decision tree. So first, so now we are in the core of the application of what we have seen in the lecture last week. So first, we will use the function decision tree from scikit-learn. So here, if I use decision tree classifier from scikit-learn, I will have this, sorry, this help page. And so this is exactly what we have seen last week. So we have some options, and I do not discuss again the option because we discussed them last week. But let me go back here. The idea is that I do not here specify the data. Why? Because, okay, there is with scikit-learn, there is a kind of a two-stage approach. In the first stage, I declare the structure of the tree. D'accord? The global structure of the tree. So here, what is the structure of the tree? So I will not explain you all the options because, okay, but let me here discuss these two options. First, random state is equal to seed, so the number 42 that I put before, but it is unclear for you maybe at this stage. So let me, I can withdraw this part, but max depth is equal to 4. So I don't mention the type, the data, so the X and the Y, made to train a decision tree for which the maximum depth is equal to 4. I can put other option. Remember, I can put some option about the criterion used. By default is Gini for the split. I can put some option on the minimum sample used to produce a split at a node. So, okay. And then I will define, using this option, I define a tree structure, a tree, a global tree structure. And then this structure is stored in a variable. And this variable is called tree, but okay, I can use whatever. Ramage or what you want. Whatever the name, I put this structure in a variable. And then with this variable tree, I will ask to Python to do some actions. First, I can ask to fit, to train this structure tree. I will use another option here later, in which I will ask to Python to make some prediction, to forecast with this tree, etc., etc., etc. So the idea is a two-stage approach. Here, I declare a structure of the model, which is stored in a variable that represents the global structure of the model. And then, with this model, I ask to Python to do some action, to fit the model, to predict, to use this model to make some prediction, etc. It's clear? So what is the syntax? So tree is equal to decision tree classifier with a maximum depth of 4, but I can also put some other option. For instance, mean sample live, okay, is equal to 2, etc., etc., okay. And then in a second stage, I ask to Python to fit this model and to store the tree that he has obtained for a given sample in a variable that is 3 feet underscore 1, whatever the name. You can change the name, okay. Okay. And then, but okay, I store the result, so the final model estimated train in this variable. So option, so 3 point fit. Then for that, I have to specify what are the feature here and what is the dependent, the target variable. Okay. So let me fit. Okay. I have a problem. It's my help. Okay, fit on the here. I have to first specify the features and then to specify the target. Okay, I have other options, but whatever. So if I run this code in block of instructions, these 2 instructions, it takes a few seconds because the sample is not so important. And then now here I have my decision tree. There is no output because, okay, I have now to ask to Python to represent this decision tree. Sometimes it's not necessary to represent the decision tree. Sometimes you just use the decision tree to make some forecast, and you are not interested by the representation of the decision tree. And this is particularly true when the decision tree has a huge is huge or with many variables because okay, it is difficult to understand and to its structure. Okay, so now with this block of instruction from scikit-learn tree, I import plot tree. So plot tree, okay, is a function that allows to plot a decision tree. So the first argument of plot tree is a decision tree that you have trained, so issued from the function point fit. Okay. So we have a 3 stages approach. First, I declare a decision tree structure. Then, second stage, I train my decision tree on a sample. And then I represent it, if I want to represent it, with plot tree. Let me go back. So plot tree, what is the first argument is tree underscore fit underscore 1. So this decision tree. Okay, so I put some options for the figure name just to, okay, to use the name of the variables. And for class name, rather than to write 0 and 1 for y, I can use some names to specify what is 0 and what is 1, okay? And then I can control for the size of the font, etc., etc. There are many options. Plot show allows you to have a direct output of your graph, okay, your plot and your graph. So this is I run this code and then I obtain my decision tree. Okay, and I will open. This is the first decision tree that you have seen, and here Okay, so this is job tenure variable as the first splitting for the first splitting node, decision node. And then if the job tenure is smaller than 2.5 months, then you are on the left. And if it's not true, you're on the right. On the left, the second variable used here is a funding amount, and the threshold is 18,000 of euros. If the funding amount is smaller than this threshold, you are on the left, and if it's not true, you are on the right. On the right, it depends on your status of homeowner, if you have your own house or not. If it's not the case, you are on the left. If you the case, you are on the right, etc., etc. It depends on the monthly payment, and then at the end, you have the final notes in which you recognize the Gini index, the samples, the values, so just to compute the probabilities, for instance, and the majority class decision. Here, you are in the non-default class. Do you have any question? No? Great. So,
Yes,
yes?
I'm asking about depends on what I choose the maximum depth equals
Yes?
4. Why 4 exactly?
No.
We didn't choose 3 or 2.
Okay, great. So, just to redo the exercise, at this stage, I don't know how to specify the max depth decision tree, but if I change the max depth decision tree, I rerun the code, and here I have a shorter decision tree. And if I put no option, so there is no limit for the maximum decision tree, okay, but I'm afraid that the representation will take some time. So we will, as you will see, the decision tree tends to be very, very deep because there is no pruning, no pre-pruning, and no post-pruning. Okay. So as we will discuss in a few minutes, we will have some strategy to fix the optimal value of the maximum depth because this is a hyperparameters, and so we have to fix it by a cross-validation approach to avoid the overfitting. Okay. So in a
Okay,
few minutes, I will discuss with you how to obtain the value. So as you can see here, the representation of the decision tree which has a large depth takes time. So don't try to represent your model if your max depth is high because okay, it will take some many minutes. For instance, I guess that it will take 5 minutes. So I have to go and then when the graph will be ready, I will go back to this graph to show you what is the maximum depth that has been chosen by the model if I put no limit here, the maximum depth, okay? And okay, so I have to rerun here with okay, the code with maximum depth, for instance, is equal to 4. Okay, so I rerun this code. Yes, but here, okay, so there is a problem, but okay, here with maximum depth is equal to 4. Okay, and then here, okay, because there are too many nodes, and when there are too many nodes, this function has some difficulty to represent the decision tree. Okay, so my warning message was about this problem. So let me go back. So I go back to decision tree with maximum depth equal to 4. And then now, this is not the optimal tree. We will discuss this point later. But now I show you how to produce some forecasts based on this decision tree. So I consider my train decision tree, which is 3_fit_1, and I ask to make some prediction. So point predict, point fit, point predict, okay? So, and I store the forecast in prediction. Then I use a data frame or whatever, okay, just to store the prediction. And I compute also what are the predict probability. So you see here, I have predict. Predict is used to make some prediction on the binary outcome. So the result of predict is a 0-1 variable. And predict probability refers to the conditional probability to obtain a 1 or a 0. Okay? And just to precise, if you want to compute the conditional probability to obtain a 1 or a 0, you use this option. And here, by writing 2.1, I explain that I want to produce a forecast of the conditional probability to have a 1. Okay, so the probability, the conditional probability to for a default. I store in a data frame that is called df probes3, and then I concatenate the prediction here and the probability here in a same data frame that is called data pred. Okay, and then I also include in this data frame the feature, just to understand what are the reasons why the model produce the decision 1 and 0. And so I display the 10 first lines of this data frame. So here, I have for the first individual, remember, there is no split between training and test data set. So the first individual is here. If I remember well, where is the first individual? Yeah. Sorry. The first individual is here. For the first individual, there is no default. For the second individual, there is a default. This is the true value. And here, for these two individuals, I produce the prediction of the model. So 0 for the first individual and 0 for the second. For the first individual, it is okay. There is no prediction error. For the second individual, there is a prediction error. And this is the prediction of the model, of the probability to obtain a default for the first individual and to obtain a default for the second individual. Do you remember how to produce this probability? For instance, let us imagine that the first individual is included in this. I don't know if you want to, so I will use paint. It is always simpler. Up. Let us imagine that my first individual has been classified in this final node. What is represented in the column probability? It is simply defined by the ratio of, so let us imagine that it is, it is in this final node. This is simply the ratio of 150 over the number of individuals that belong to this final node, so 640. Remember that given this value, I can produce the probability, estimated probability by the model to obtain. Okay, and if my new individual is affected to this final nodes, then okay, the probability is simply defined by the ratio of the credits that are default to the total number of credits that belongs to this class. So let me go back. And here, but okay, I have the variables that could explain the choice. And if you want to understand why this individual has been classified like this, okay, I consider the job tenure, and here the job tenure is equal to 34. So the first condition on the obtainer is not true. So we are on the right. Married. So my individual here is married. So this is false here. If there is no opposition, I propose to take a break of 10 minutes. Okay. It is called train test split. So this is also a scikit-learn function that allows you to automatically separate to create a train test and a test set from your initial data set. So what is the syntax? I have to specify here X and Y, so the arrays that I want to split. I want to split the X, so the features, and I want to split the Y, so the target variable, into a train test and a test set. And then I will store the features of the train and the target variable for the train data set, and the feature for the test set, and the feature for the target for the test set in this variable. So X underscore train, X underscore test, Y underscore train, Y underscore test. So I want to split X, I want to split Y. The test size represents 30% of the total size of my initial data set. So the train set represents 70%. And then it is particularly important here to fix the random state. So I use my value seed. So you can write here 42, but okay, if I want to change the random seed in many functions, I prefer to store the value of my seed in a variable. Okay, so but I can change whatever the value. You have to fix it, because if I want to redo exactly the same split tomorrow in 5 minutes, then here, thanks to this option random state, it allows me to fix the seed of my random draw. The stratification, there is an option here, stratify. What is the option stratify? So if not known, okay, so if you put something, your data is split in a stratified fashion using this as a class label. So what does it mean? It means that I want to stratify the random draw according to Y. So remember, Y is a default, non-default variable. This is a binary variable for which I observe only 20% of one, okay, 20% of default. If I use the option stratify, then what does it mean? It means that, okay, I have two samples, so my train sample and my test sample. The fraction in my test sample and my test sample, the frequency of default will be exactly the same and will be also equal to 20%. Okay? This guarantee means that, okay, the fraction of default will be the same in the two subsamples and in the total population or initial sample. Okay, so now I have stratified, so you can, what is, okay, for instance, I can ask, oh, sorry. The number of individual in my X-train sample. So I have 5,200 individual in my train sample, and in my test sample, I have 2,232 232 people who credit in my test sample. So now let me redo the estimation of a decision tree on my train sample this time. So first, let me declare a decision tree classifier. This is also tree, but in this state, so I store in the same name. So it, if I run this instruction in the tree, I will store this last version of my decision tree classifier model, okay, for which I put my maximum depth of 15. I control for the random seed, and then I ask to Python, to scikit-learn, to fit this tree structure, but this time I use X-train and Y-train. So I use my training sample. And the result is stored in a new decision tree that is called 3_fit_2. Is there any question? Okay. I put the maximum depth to 15 just to illustrate you the problem of overfitting. Because if I let the model choose a decision tree with a large depth, okay, then the risk of overfitting is increasing. Remember, I have with a large depth, I have a low bias, but a huge variance, okay? So this is the visualization of my decision tree, which has been trained on the training sample with a maximum depth equal to 15. So it will take a few minutes, but okay. Okay. And then here, I will do the prediction of the train, okay, using the tree_fit2, so the models that have been trained on the training sample. And then, and this is the way to illustrate the overfitting, I make the prediction, so I will compute as the 0-1 forecasts, but this time on the test set. So here on the train, here on the test. And so I have the prediction on the test, and I have the prediction on the train. I compute the probability and the prediction probability on the test, okay? And then I store all this information. Just it makes a few minutes to run this part, so the code may break, but okay. So this is my decision tree. As you observe, the decision tree with maximum depth equal to 15 is difficult to read. Okay, so it's really, there is a difficulty to understand the structure of the tree, but whatever, this is not my problem at this stage. Okay, that's why in general, we do not reproduce the decision tree. This is particularly rare to print the structure of the tree, because even with 15 depths, okay, it's difficult to understand the structure of the tree. But whatever the structure, here I can run donc this part. So I have my prediction train, my prediction on the test, my probability on the tests, and here I store in data pretest both the prediction on the test and the probability on the test. So this is in the X. So this is exactly the same graph, the same table that I presented to you before. But this time, the difference is that the model has been trained on the training sample and evaluated and used to produce forecasts on the test sample. So for instance, for the individual with this number, okay, the prediction is 0, whereas the true observation is equal to 0. And this is the probability to have a default. Here, the model predict 1, this there is a 1, a true 1, and the probability to predict 1 is equal to 1, etc. So let me now compute the accuracy. So to compute the accuracy, I have to compare the Y and the prediction. And I do this comparison on the training sample. So I compare Y train to prediction train. This is the same on the test. So I compare the Y on the test and the prediction on the test. Okay, and this is the same for the IUC on the train and the IUC on the test. So this is exactly the same instruction as before, except now that I compute the accuracy measures on the train and on the set. What is your conclusion here? If one day you have this type of figure, this type of configuration, what is your conclusion?
I think that the model is very complex, that is working very well with the train set, but it doesn't work really good for the test.
And what is the name of this phenomena?
Yeah, it's the overfitting problem.
Yes, exactly. So this is typically a problem of overfitting. So the model that you train on the train set is very complex and is very specific to the data that you use, because you allow a huge complexity of your model. And here, for instance, there is a guy with a man that owns its own house, etc., with very particular guy and on this final note. Okay, and it is likely that this guy will not be present in the test set. And so your model is very well suited for the data on which you train the model, but there is a lack of power of generalization. And then when I will use this model with new data for the test set, then the accuracy will decrease. So, and here it is particularly impressive because on the train set, the percentage of correct classification, so your model predicts 0 if there is 0, and 1 if there is 1, is 96%. But if I use exactly the same model to predict on the test set, then, so in other words, for new data, then the accuracy decreases to 74%. Okay. This is exactly the same for the IUC. So here you have the IUC, which is 0.999. What does it mean? It means that if I stay here, I say, oh, I have a perfect model because, remember that the highest IUC that you can obtain is 1. Okay, what does it mean, 0.99? It means that, you have a near perfect model. But it is not true. It is an overfitting issue because in general, when you have a very high IUC, it means that you have an overfitting. And if I use this model, the IUC on the test set, on the new data set, is only 0.60. So I write a function which is called modelization that use a model, so the decision tree, that use a train, that use a X for the test, a Y for the train, a Y for the test, the depth of your tree, and that run automatically this accuracy. So what does it mean? It means that this function run, what does it mean? It do this type. So, I have a train and a test, so this is done. So my function, modelization, do this decision tree classifier instruction, do the fit, do the prediction of the train, the prediction of the test, compute the accuracy on the train on the test, the IUC on the train on the test, and display the result. Okay, so this function do everything from here. Okay, not the representation, all this block of instruction, and all this block is instruction. Okay, so but this is just written in only one function. Okay, that give me what is your train, what is your test, give you what is your type of model, what is your maximum depth, and then directly I display the accuracy on the train, the accuracy on the test, etc. Do you have any question about this function? It's just a way for me to reduce the size of the code. Okay. Okay.
Excuse me.
Yes.
What does DT at the beginning of the line represent? DT and then accuracy.
DT is a decision tree. So I store
decision
in
tree.
the first variable the model that I've been trained on the trained data set.
Thank you.
Okay, so I want to make a loop, and just to illustrate this idea of overfitting, I will do a loop on which variable? I will make a loop on the maximum depth. Okay, so here you have a loop for the depths in NP range 1 to 21. What does it mean? It means that I will consider all the maximum depth from 1 to 21. And then I run my function modelization. So the result of this function in my decision tree with 1, 2, 3, etc., 21 maximum depth, I consider my accuracy on the train. I have as a result the accuracy on the test, the IUC on the train, the IUC on the test, and then I stored on this result in some tables, and I display the result. This is clear? Let me illustrate. This is the depth of the tree, 1, 2, 3, 4, 5, 6, until 10, but you can, okay, put 21, 20, sorry. And here I have the accuracy on the train, the accuracy on the test, the IUC on the train, and the IUC on the test. What do you observe? You observe that when I increase the complexity, so first, let me consider a very simple decision tree. There is no difference between the accuracy on the train and the accuracy on the test because there is no overfitting. So the accuracy are very close each other. The IUC is the same. But the accuracy is poor. When I increase the complexity of the model, the accuracy tends to increase. Okay, and I want to increase the accuracy of because I want to forecast better the default. But in the same time, so I observe that when I increase the maximum depth, the accuracy and the IUC increases, and this is particularly true for the train, but also for the test. But I observe also that, okay, I have a divergence between the accuracy of my model on the test and on the train. And this is the idea of overfitting. And I want to check, I want to determine what is the optimal complexity. So what is the optimal depth of my model, okay? So I consider the result that have been, okay, so on the depth, on the accuracy, and just I put them on a graph. So here on the x-axis, I have the depth of the tree. On the y-axis, I have the accuracy, so the percentage of correct classification on the train and on the test. So according to you, what is optimal model? What do you recommend me in terms of depth or maximum depth?
7. 7
yes.
is good.
Yes, 7. Yes, yes. Because after 7 the accuracy tends to decrease on the test set, and this is reasonable in terms of difference between the train and the test. And there is a short decrease, a small decrease, but there is no overfitting issue. Okay. When you compare, so this was the graph of the accuracy. I reproduce the same graph with the IUC. And according to the IUC, the optimal model tend to be less complex, and the criteria of the IUC tends to recommend a model with a maximum depth equal to 5. Okay. Well, I recommend you to use the IUC in general. We use the IUC rather than the accuracy, but okay. So if you want to determine, this was a question to determine the optimal. At the beginning, you remember I put maximum depth is equal to 4, okay? Well, I have no idea about that, okay? What is the optimal model? So the first way to determine the optimal model is to do this work, okay? To do a loop, to estimate all the models, to compute all the accuracy, to reproduce the accuracy on the train, on the test, and to say, okay, my best model is here, okay? The second approach is the approach that I taught to you is based on the cross-validation. And here we will use the cross-validation based on the grid search CV. So grid search CV is a function of scikit-learn. CV for cross-validation. Grid search means that I will consider a grid value, a grid of values for my hyperparameters, and I will assess all the values on this grid. Okay, so for instance, the maximum depth in my hyperparameters, I will define a grid from 1 to 21, and then I have a loop that take a value 1, 2, 3, 2, and 21. And for each value, I will compute the cross-validation error. So let me consider a tree object in which I store my decision tree classifier structure, and I declare a grid of parameters. So I can use other parameters, but okay, here I just want to determine. Remember that in my decision tree, I can use a minimum split, I can use a minimum sample length, I can use a minimum weight, no, not this one, the maximum depth, okay, as hyperparameters because it controls for the complexity of the model. Here, I will only focus on the maximum depth, and this is that we generally do in general from decision tree. So my hyperparameters is maximum depth. And I want to check all the value between 1 to 16. So here I have a grid of value on these hyperparameters. And then what is the syntax of the grid search? So the grid search CV, I use my tree because this is my model. I use my grid of hyperparameters. This is my grid of hyperparameters on the maximum depth. Here, CV is equal to a value, and CV determine the cross-validation splitting strategy. So, other word, in all cases, grid search use a scaffold approach. You remember? The scaffold approach means that, okay, I have to split my train test, my train test into 5 folds, and then I have a loop to use alternatively them as to train the model and to evaluate the model out of sample. So here, if I put CV is equal to 5, I use a scaffold cross-validation approach with 5 false. End jobs, it's just end job. It's an option to use end job. It's a number of jobs to run in parallel because it is okay. As I mentioned to you, the cross validation, especially the grid search, may be very time consuming, and that's why I recommend you to to use some option to optimize and to use many jobs. But okay, we are on the cloud, Google Cloud, so there is no problem in general. Okay, but okay, end job is an option to control for the parallelization of your code. Scoring node is an option. I don't have to detail. Fit, where I want to do my scaffold. Remember, I have to split my training dataset into 5 folds. So I use X-train, Y-train. So grid search, point fit, X-train, Y-train will give me a model fit. Okay? And the model fit, what is the outcome of the model? Huh? What is the outcome? It's a model with, okay, the optimal parameters. Okay? So model fit, in the model fit, I store the optimal decision tree with the optimal depth determined by cross-validation. Do you have any question? You remember well the idea of cross-validation, or do you want that I go back to the slides to explain the idea? No? If you want to check what is the value of the optimal depth for the optimal complexity determined by the cross-validation scaffold with 5 folds, okay? So I consider my model fit, so my model, and I use the instruction point best estimators. It gives me what is the optimal value of the parameters that I declare, for which I declare the grid here. So here I have only the maximum depth. If I have 2 parameters, it will give me the 2 optimal values for the 2 parameters for which, hyperparameters, for which I am trying to determine the optimal value, okay? So let me run this part. So as you can observe, even on the Google Cloud, it takes 2 seconds, to run. And you observe here that the optimal model is obtained with a maximum depth equal to 4. So it is close to the IUC here that you have here, okay? It is the optimal value given the cross-validation obtained with a scaffold approach is a model with a maximum depth equal to 4. Do you have any question? No? Okay, so model fit CV result is just to show the result of the cross-validation. I'm waiting a few minutes, a few seconds to get the results. Well, yes. Okay, I want to skip this part because, okay, it's not really important. What is important is the fact that, okay, the cross-validation allows you to determine the optimal value of the hyperparameters, so the optimal complexity, and the optimal complexity, given this criteria, is obtained with maximum depth is equal to 4. I guess that the results are based on the IUC. I think that it is this scoring option that it is determine the, I don't remember the scoring option, grid search, scoring, what is the scoring option? Scoring, score, to score. Okay, if it's just the way that I compare, because I can compare the cross-validation in terms of classification error, etc. So this is the score that is used to compute the cross-validation error. But for this validation error definition, maximum depth, optimal maximum depth is equal to 4. So I consider now this model fit, which is the best estimator, which is a best model, and then I can show the optimal model. Okay, represent the optimal model. So this is the optimal model. This is the same model that I obtained with 4 the maximum depth at the beginning, because okay, but this is now I know that it is the optimal model, and it is answer to the questions that have been presently. I can do the prediction of the train, the prediction of the test, and I can evaluate the accuracy. And what is your conclusion now that I have determined the optimal model using cross-validation? Now, there is no problem of overfitting. Is it clear for you, this idea of overfitting and the use of cross-validation? Is there any question? You observe that the accuracy on the test and accuracy on the train are very close, and they are very high, and so the model is good, and there is no difference when I use this model on new data. Okay, the accuracy remains stable. Okay, I propose to not now interpret the importance of the variable, because I will discuss this point when I will present you the random forest. Is there any question about the code and this illustration of what is overfitting, how to control for that? And now, if you want to implement in practice a decision tree, then you just have to use this part. Okay, so I declare the decision tree. I declare my hyperparameters. Typically, in general, this is the maximum depth. I made a grid search to determine the optimal value of the hyperparameters. So here, in the model fit, I have the best estimator, okay, the best model. And then I can produce, if the size of my decision tree is limited, I can represent it and analyze the decision rule. And otherwise, I have just to use it to make some prediction on the test on the train, and then to check the accuracy of the model. Is there any question? No?
I have a question here. So whenever we are talking about accuracy, we mean like the goodness of fit if we are talking with the econometrics terms. So is there any other things to do to test our decision tree if it's working good or not? Like something like the confidence of interval, if the model is biased or not. Is there something like this?
Okay, good question. Okay, so there is a second difference between econometrics and machine learning. Is the fact that in general in machine learning there is no inference procedure. So there is no question about the significance of some parameters, okay, etc., etc. So I have I have some parameters. Remember that I have some parameters. These parameters are the threshold here. 20, for instance, on these nodes on age, there is a threshold on 24.5, okay, years. This is the parameters, but in general, we do not discuss. There is no discussion about the test, about an inference procedure, about the value, if it is equal to 0 or not, etc. This is not the way we proceed in machine learning. Okay, so in machine learning, we have at the end some goodness of fit values. Okay, so if it is a regression, we have some R squared, we have a MEC. Okay, for classification problem, we have a Gini index, IUC, accuracy, false positive rate, etc. So there are many measures to check if the model is good or not. But this is only the way we evaluate a machine learning model. Okay, but we make a very careful treatment about the fact that we evaluate the model, we assess the model out of sample on a test sample. Okay. Is there other question? No. Okay.
Excuse me.
Yes.
I have a question about cross validation, scaffold cross validation.
Okay.
Is it possible to use it when we work with time series?
With the time series. Great. Good question. Okay, there are specific cross-validation approaches with time series for which there is a dependence between the series. Okay, and so there are some specific method of cross-validation for time series model. Okay, or time series.
Okay. So we cannot use scaffold for time series. Okay.
Yes, in general, no, because when I will use this part of the data, etc., and the way you split the data at the beginning, and even, for instance, very simple, at the beginning, I split the data between a train and a test, okay? In general, with time series, this is not a random drawn, okay? Because, okay, I just say I will use the year 2020 as a test set, and the data from 1980 to 2019 as a trained data set. Okay, so there is no the idea of random data of a random draw. Okay.
Okay.
And this is exactly the same for the cross validation.
Okay, thank you.
Is there other question?
So apparently there is a trade-off between depth and precision when choosing the optimum length of the decision tree.
Yes. Yes. Remember. Yes. Sorry. Excuse me.
So we can instead of choosing a random like depth from the beginning, we can run the loop and let the algorithm choose for us the optimum depth of the decision tree, right? You can do that.
Exactly. So I remember that, okay, what we have learned, okay, the fact that if the depth increases, okay, it has two consequences. First, it decreases the bias, but it increases the variance, okay? And this is the illustration that we have here, okay, is the fact that we have a high variance means that for new data, we have a lower predictive quality, okay? And what we have done with the cross-validation is to determine the optimal complexity of the model in order to make the optimal trade-off between the bias and the variance. I'm not sure to well answer to your question.
Yeah, you did. Thank you.
Okay. And in general, I recommend you to not fix by yourself the hyperparameters, because otherwise the risk is that to observe an overfitting issue is the fact that, okay, a decrease of the accuracy between the test and the train test. But don't hesitate if I don't really answer to your question. No, it's okay.
Yeah.
Okay.
So if this wasn't like an exercise for us, you wouldn't do the same steps. You would like from the beginning ask like Google Colab or Python to give you the optimum depth.
Yes.
Okay.
Okay, so I propose, if there is no question, I propose to take a second break, and then we will go back to the theory, and I will introduce you the ensemble method, and we will start with more sophisticated models that will give you more efficient estimation for the regression or classification. So especially the random forest model. Okay, so propose to take a break of 10 minutes. So we have time now for to start the last section devoted to ensemble methods. So just I want to warn you that, okay, this section is a little bit more complex from theoretical point of view than the first part. It is particularly true for the boosting, okay, but also for the bagging techniques. So I will try to explain very simple way, and then tomorrow we will apply. I guess that I will have time to apply the random forest, but not the boosting method. But okay, I will give you the syntax to estimate an XGBoost model. So if it's okay for you, let's go with the ensemble method. So what are ensemble methods? So it's a set of machine learning algorithms that are all based on the same idea. This idea is based on the aggregation or a combination of a large number of model of learning algorithm. And this is the idea to combine weak learners, many weak learners, for instance, a decision tree, a decision tree, a decision tree. I combine them and I obtain a strong learner. Okay. And it has been demonstrated that, okay, this method generally improves the predictive quality. So you get better IUC, better accuracy for a classification problem, or better R2. Excuse me, better R2, etc. On a regression problem than if you use what we call weak learner, for instance, the decision tree, for instance, SVM, for instance, whatever, linear regression, logistic regression, or whatever. This is an old idea in econometrics. This is the idea of the combination of model. Okay, this is the idea. Okay, I have to make a prediction. I have to, for instance, for regression model, I use many regression model with, for instance, in the first model, I include 3 variables. In the second, 4 variables. In the third one, 10 variables, etc. So I have many different models. I use all these models to produce some prediction. I combine this prediction and I get a combination of the forecast, for instance. This is an old idea. And it is true that is, okay, the idea to combine the forecast of many models give you a more robust prediction, a more robust model. What is mean? It means that when I have an outlier, when I have a very particular behavior of a part of my sample, then my model is still correct, okay? And this is the idea to reduction of the variance of the model. Okay, this is the fact that my prediction, my model is more robust. It is related to this idea of reduction of variance. Okay, there are many methods of ensemble methods. Okay, there are homogeneous ensemble method, heterogeneous ensemble method, whatever. But okay, we can distinguish three types of method: the bagging, the boosting, and the stacking. Okay. Okay. The bagging method. The bagging is an acronym based on two words: bootstrap and aggregation. Okay. It's a method that is used to improve the predictive quality of model with low generalization power, with high problem of overfitting, okay, such as decision tree. And the boosting method are based on an adaptive strategy to boost the predictive performance of any type of model. Well, in general, we apply the boosting techniques to decision tree. So we have a boost tree model, okay, but I can boost the regression of the result of a linear regression model. I can boost the logit, I can boost SVM, I can boost anything, okay? Within this method, so within the bagging, there are many algorithms. For example, you have a rotation forest, random forest, whatever, okay? The most often used algorithm is a random forest. Within the boosting techniques, there are many boosting models or boosting algorithms, like gradient boosting machine, extreme gradient boosting machine, adaptive boosting, AdaBoost, etc. So I will present you the AdaBoost because it's the simplest algorithm. But the most often used algorithm in the boosting family is the extreme gradient boosting method, which is the XGBoost. Okay. So let me start with the bagging. So the objective is to understand the general principle of the bagging, to know how to build a bootstrap sample, to understand the advantage of the aggregation of these weak predictors, to understand what is this idea, main idea of the bagging is the reduction of the variance. And we will discuss this point. We will use the majority vote rule, and we will also define a notion of error, which is error out of bag. And we will discuss a problem, which is the first algorithm that I will present to you, in which the model is non-interpretable. So this kind of black box between the X and the Y. I don't understand what is the link. And then I have to implement some method to understand what is the influence of the salary of the age on the outcome of my model. So we will introduce what we call the feature importance. So, okay. The bagging was also introduced by Leo Breiman, so the same that I introduced the CART algorithm in a paper in 1996, bagging predictor and machine learning. And bagging is an aggregation of two words. So I have to understand what is a bootstrap and what is an aggregation, okay? So let me illustrate the idea. Is very simple. I have my training data set. From my training data set, I draw random samples with replacement. I draw a first sample with replacement. I draw a second sample with replacement. I draw B sample with replacement. When I draw a sample from a population or from an initial sample with replacement, I do what we call a bootstrap sampling. The idea of the bootstrap is to draw with replacement. Okay? So this sample issued from the initial sample are draw bootstrapped sample. For each bootstrap sample, I train a decision tree. So I have a tree here, I have a tree here, and I have a tree here. Contrary to the representation on this figure, the trees are in general different. Why? Because the individual here are not the same as the individual here. And so the tree are not exactly the same. Okay? So now what is the idea? The idea is that, okay, I consider a new individual with some feature, age, funding amount, car price, etc. I will use this tree to predict if there is a default or not for this individual by using this third decision tree trained on the first bootstrap sample. It will give me, for instance, y hat is equal to 1. I consider the same individual. And I use this decision rule. The decision rule issued from this second decision tree. And this decision tree said, okay, there is also a default for this individual, etc., etc. I use this decision tree trained on the last bootstrap sample. And given the characteristic X of this individual, the forecast obtained for this individual is 0. So I have B different prediction forecast for my individual here on the test sample. And then the second stage consists in using an aggregation of these forecasts. The most easy way, easy to understand, is a majority vote. Okay, if I have 100 bootstrap sample, and from 19 of them, the forecast is 1, and for 10 of them, the forecast is 0, then the majority of the forecast is 1, and so the aggregation say, okay, for this guy, my prediction is 1. It's clear? This is the idea of the bootstrap. This is the aggregation, the bagging of the bootstrap and the aggregation. Okay. Is there any question? Okay, so let me rewrite the idea with a more formal way. We construct B estimator on bootstrap samples and we aggregate them. So I have a train sample, x1, y1, xn, yn. This is a training set of size n. First, I draw B, capital B, bootstrap samples of size m. The size m can be equal or smaller than the initial size of the training samples. We draw this bootstrap sample with replacement. What does it mean? It means that, for instance, I can have 2 or 3 Christophe Hurlin and 2 or 3 Mireille Maher in the samples. Okay, because this is with replacement. Each observation has the same probability to be selected. This is an uniform sampling. So we can have n example from the train, m example with m smaller than n. Okay, there are 2 methods. I will introduce you an option to distinguish between method A and B. And so what is, for instance, here, the size of the bootstrap sample is 5. The size of the initial sample is 10. Okay. And this is my idea. So I have a sample in which I have 1, 2, 3, 4, 5, and 10. Okay, my individuals. And then in my first sample, I have individual 2, 3, 6, 8, 4. Okay. But this example is not very interesting because, for instance, we can imagine that, okay, we have 2 times the individual 2 in the second sample bootstrap, okay? And here, M is equal to 5, N is equal to 10, and we are in second, in the case in which M is smaller than N, okay? So we draw random subset, so my bootstrap sample, bootstrap. In general, the number of random of bootstrap samples that you have to do, in general, I recommend you to use it as the hyperparameters of the random forest. Remember, for a tree, the hyperparameter is general the max depth, okay? But I recommend you for a random forest to consider that the number of bootstrap be as a hyperparameters. But for each bootstrap sample, D train B, we train a model, typically a decision tree. And I denote H at B, the model that has been trained on the B, on the bootstrap sample B. Then the prediction of the meta model, so bagging, is obtained by averaging the output for regression or using a majority vote for classification. This is the aggregation phase. Let me define the case in which we have a regression. So the hypothesis, so the model, resulting from the bagging procedure correspond either to the average of the estimated model I h at B. So the bagging, the final model, is simply the average over B, so the sum from B is equal to 1 to capital B, of all the decisions done by the model. So, for instance, if I have a regression in which I try to predict the price of the house for a given house, okay? So for a given house, XE. So this house has a particular specification, the size, age, whatever the location, okay? For this precise house, I train B models that gave me some prediction of the price. So the first model gave me 1 million, the second 2 million, the third 100,000 euros, etc. And then the final decision, the final prediction for this precise house is simply the average of the forecast given by all the models. When you are in the classification, the decision for a particular firm about the fact that to default or not, okay, is simply the majority voting rule apply to all the decisions done of classification done by all the models, okay? Okay, sometimes in the classification, you have also an aggregation based on the odds ratio, but the odds ratio is the probability to have a 1 divided by the probability to have there is a typo, this is a minus here, to have a 0, okay? This is a ratio between the probability to have a default and non-default. And then in general, you can compute the odds ratio for all the individual obtained with all the models trained with all bootstrap samples. And then, in general, the model bagging will average the odds ratio obtained with all the submodels. Okay, this is a subtlety. You can use a majority vote or use the average of the odds ratio. And then from the odds ratio, it is possible to deduce the probability, and from the probability, you put a cutoff at 50%, and it depends if the probability is higher than 50%, you predict a 1. Well, the majority rule is very simple. It's the fact that, okay, the majority rule is the fact that, okay, you have each model give you a 0-1 prediction, for instance. And then, for instance, let's just imagine the first model give me 0, second model for the same individual give me 0, and the third give me 1. And so this is the mode. And so we have more 0 than 1. And so the final prediction is equal to 0. So let me say again the same thing. So I have a training data set. I have some subsample issued from Bootstrap sampling. For each, I train a tree. Here, you observe that the tree are not the same. So the tree here is not the same as here, okay? And now, what is on this representation? I have an individual, and for this individual, okay, given its characteristics on this tree, okay, I obtain this final decision. And for this final decision, for instance, it is the final forecast is class A, for instance, 0, okay? For the same individual, using the second tree, okay, given its characteristics, okay, the final decision for him is here, and is, let us imagine that is majority class within the final nodes is B, etc., etc. On this tree, okay, the final nodes for him is here, and in this final node, the decision is class A. So I have all my forecasts given with a Bootstrap sample, and I use a majority voting rule, and then my final class in here, for instance, is A. Okay. Do you have any question? No? So it's really easy to understand what is the bagging. A question now is to know why we should use bagging. And we should use bagging because it allows a reduction of the variance. And to understand this point, I have to introduce some notations. So remember that H at B is my model, or more precisely, the forecast of my model trained on the B Bootstrap sample for Christophe Hurlin. Let me now introduce two notation. I introduce the variance of this forecast. Okay, it depends. When Christophe Hurlin or another person, the variance, the forecast, for instance, let us imagine the price, the forecast price by my model depends on the characteristic. And so given the characteristic, XE, there is a variance of the price that is forecast by my model HB. All the models are different, okay? But I assume that the variance of each individual model is the same. Let me go back here. The variance of the forecast issued for this model is the same for the variance of the forecast of this model. It doesn't mean that the forecasts itself are the same. It means that the variance is the same, okay? So I denote by sigma squared of xi the variance of the forecast of the model trained on the Bootstrap sample. And as you observe, there is no B. There is no B index. Why? Because the variance is the same for all the models. I now also introduce the correlation between the model trained on the B sample and the model trained on the S sample. Okay, I consider Christophe Hurlin I use the first model to make a forecast for his price or price of his house. I use the second model for forecast the price of his house, and then I compute the correlation between the forecast of the two models. This is the same. We can show that the models are identically distributed, and given this assumption, the correlation is the same. So if I consider the correlation between the first model and the second model, it is the same that the correlation between the first model and the 10 model, okay? There is no index B and SR. So I have the variance of the forecast. I have the correlation between the forecast of the individual bootstrap sample. The main result of the bagging is the following. The variance of the bagging model, so this is the variance of the final model, is equal to this equation. It corresponds to the correlation times the variance of the individual model, plus 1 minus the correlation divided by B, the number of bootstrap samples, times the variance of the individual, okay? Let me just show you the proof. It's very simple. Huh? So I have the variance of the bagging, and the bagging is simply the average of something. So this is the variance of a mean. So when I have a variance of a mean, so remember that, okay, first I have to, okay, look, the B here become a B squared here, okay? And this is the variance of a sum, okay? And the variance of a sum, I have the two terms of the variance, huh? Variance of X plus variance of Y, okay? Plus 2 times the covariance, okay? This is exactly what you have here, except, okay, this is not writing in the same way, but whatever. The variance of the mean is 1 divided by B squared times the sum of the variance. So variance of the first model plus variance of the second model, etc. Plus 1 sur B squared, a double sum, B from B is equal to 1 to capital B, and S of difference of B of the covariance. The covariance is the correlation times the variance. Okay. So we have here and here. Oh, I have the B squared, okay, which is here. And here, this double sum is simply equal to B minus 1 times B, okay? So on the left, I have 1 divided by B squared. And here, I have a sum of the variance. The variance is always the same. So it's the variance plus the variance plus variance. So it's a B times the variance. So here, I have B from times sigma squared divided by B squared. So the B disappears, okay? So it's very simple, okay, to get this result. Now, let us imagine that I use a large number of bootstrap samples. So B tends to infinity. Then this part disappears. What is the variance of my bootstrap, of my bagging, is the variance of my tree, of each tree, times the correlation between the different tree obtained on the bootstrap sample. Why is very cool to get this result? This correlation, the correlation between the forecast given by the first model, the second model, etc., is always, in general, this correlation is smaller than 1. So what does it mean? It means that the variance of my bagging is smaller than the variance of my decision tree. Yes, Ahmed?
Okay, so thank you for this opportunity. I would like to ask, this is the result about the variance. What happens to the bias? Is there some kind of result
okay.
that tells us what happens to the bias?
You want the end of the story. So, okay, so the bias does not change. Why? Because we have a mean. Okay, so the bagging is a mean. Okay, sorry, the bagging here is a mean of the forecast issued from the model. And the bias is related to the expectation. The expectation is a linear operator. And so the bias is approximately the mean of the bias of the model. So if you have a model with low bias, the bagging will have a low bias. If you have a model with high bias, you will have a high bias. And there is no reduction in this part. Okay? So in other words, the bias of the bagging is approximately the same. This is mean, but okay, this is the same as the bias of the initial models.
Okay, but I find this somewhat suspicious that we are getting something, say, for free. That we are getting a reduction in variance without any kind of negative consequence.
Exactly, but this is you have fully understood the trick of the bagging, because by using the bagging, you don't have any gain, but any loss, also any loss in terms of bias. But by simply using the bagging, you reduce the variance. So you can have a model without that allow you to reduce the overfitting. Let us imagine that you have a model with a low bias, very complex. Donc low bias, it works well on the training data set. But okay, when I use it on the test set, the variance is huge, and so okay, I have a decrease of the accuracy, etc. If I use a bagging, I have the same bias. So on the training data set, there is a high accuracy, no problem. But when I use it on the test set, due to the fact that the variance is reduced, I have less overfitting-ish problem than with the initial model.
So the only cost I'm incurring is the computation time?
Yes,
here?
exactly. Exactly. That's why this is one of the most often used model in economics and finance. So the random forest, because it gives you high accuracy and low overfitting issue, etc. This is why in the most often used model, you remember, in my first slide, I give you a kind of LinkedIn post about the most often used machine learning algorithm, and in general, random forest and XGBoost for other reasons are among the most often used machine learning algorithm. Okay.
Okay, thank you. Thank you very much.
So let me illustrate. Okay, this ID. Okay, here, this is take regression of the X is the ozone concentration and Y is the temperature. So in blue, you have the true point, okay? And okay, let us imagine that you have a model, whatever the model, maybe it's not a decision tree, but whatever, okay? And this model gives some forecast of some fits given by the lines in gray, okay? So you see the line in gray, and you have, as you can observe, sometimes, okay, the line in gray are the variance is important because, okay, they try to capture some specificity of a data set. And in red, the red line, so the red line here, sorry, the red line here represents the bagging fit that simply correspond to the mean of the fit obtained by the submodel, okay? And as you could observe, there is less variance, less variability in the bagging fitted, whatever the model, the underlying model, but okay, there are less variance, okay? Let me illustrate with this, okay, also experiments. So here, we have y, sorry, which is a function f of x plus epsilon, an IID term, okay? So in blue, you have the true f function. It's difficult to see it because, okay, you see here, because there is no difference between the fit and the true value of the, so this is a data generating process, okay? This is a simulation in which I simulate a function f, and the f is unobserved, unobservable, and then I try to, okay, to infer it, to estimate it by using y and x, okay? Point. Okay, so, okay, you have the true f here. You have the points, okay? Once in blue, here, etc., in which, for which I had the error term, okay? And then in y, I have the fit obtained with a tree, and the fit obtained with a bagging tree, okay? And in the bottom panel, I have the error, and you remember that the error is the bias squared plus the variance plus the noise, the sigma epsilon, which is sigma epsilon, or sigma squared epsilon. So the variance of the error term, okay? So here, in red, you have the error. In blue, the bias squared. In green, the variance, okay? What is the difference between a tree and a bagging tree? As Ahmed said few minutes ago, there is no difference in terms of bias. You see the blue là? There is no difference. Where is the difference? The difference is the variance of the tree here. Okay, variance of the tree. Let me illustrate here. Up is here. So this is my sigma squared in my notation is larger than the variance of HB, which is the variance of my bagging tree, which is here, due to the bagging effect. Is clear? So the variance of the bagging is the correlation times the variance of the initial model. And so since the correlation is smaller than 1, it is smaller. And so at the end, the error is also smaller. That's why I have better properties, etc. Have you any question about this point? Great. So if rho is smaller than 1, the bagged estimator has smaller variance. One strategy, could be a question, but one strategy is to bag some model which has the lowest possible bias. In general, when I have a small bias, I have a high variance. But the bagging reduces the variance. So at the end, I have a small bias and a small variance, a reduced variance. But okay, there is a limit because caution, using estimator with a low bias implies that the variance will be high. It is true that the bagging will reduce this variance. Okay, but let us imagine that, okay, at the beginning, you have a small bias, okay, which is very small, and a variance, okay, var, which is big. When at the end, for the bagging, after the bagging, I will have the same bias and a reduced variance. But when I'm big, reduced after reduction, maybe I will still will have high variance, okay? So it is a reduction. It doesn't mean that I will have a small variance at the end. So don't push too much this idea to have a very complex, for instance, decision tree to get a very small bias, because the counterpart is the fact that variance is so huge at the beginning that even after the reduction, the variance will still important. But just to see if you have understood the intuition, do you think that it is, for instance, if I bagged some trees, what is your recommendation about the maximum depth option that I have to in scikit-learn? What is your, yes, Ahmed?
We should increase it. We
Yes.
want a model with very low bias.
Yes.
Well, we will have variance, but it will be decreased by the bagging.
Yes, exactly. At the limit, I recommend you to put no constraint about the maximum depth. Okay, so I let the option in scikit-learn without no limit. Okay, about the maximum depth. Okay, and so given we'll obtain a model with low bias and I guess a reduced variance. Second remark. What is the trick? The trick is to play with the correlation. The more the weak learner are decorrelated, different, the more the reduction variance will work. If I have the model 1 that gives me exactly the same predictions as the model 2, the model 3, etc., at the end, the correlation will be close to 1. And so the reduction of the variance will be small. On the contrary, if the model 1 say, okay, the house price is 100,000 euros, and the model 2 say, no, it's not 100, but 10 millions. Okay, so there is very different decision from the different model. Then the correlation will be small, and okay, I will have a great reduction of the variance. So let me go back to the intuition of the, okay, of the bagging. How to get a very different decision tree here, here, and here. For that, you have to bootstrap sample which are not similar. Okay. The more these bootstrap samples are different, the more your decision rule train on this different bootstrap sample will be different, and so the correlation will be small, and then the bagging ID will work. Okay, I have to decorrelate the weak learners. Any question?
So if we choose a bootstrap sample, which is M is less than N, we can get to a less correlated samples?
Yes, exactly. Exactly. Some
Thank
people say that, okay, when I use M, which is small compared to M, then each subsample will consider individuals that are not representative of the whole population, and so it's the initial population, and then it's a mean to decorrelate the weak learners. Okay. But the second point is the fact that, okay, you have the bootstrap sample, and then you have a model, okay, which is trained on each sample. And the idea is to compute the correlation, to minimize the correlation between the two, okay? Let us imagine that, okay, this sample is very different from this sample. For instance, I have 0, 0, 0, 1, 1, 1, 1, and okay, for a given feature, okay, on this one, I have only the 1, 1, 1, 1, 1, 1, okay? Let us imagine that the two, but let us imagine that this model are not sensible to the perturbation of the sample. Then the correlation will be I. And this is what you obtain, for instance, with linear regression model or logit regression model. Let us imagine that I have two bootstrap samples in which I change 10% of the observation. So I have 19% of the observations are common and 10% are different. If I apply a linear regression model on sample 1 and sample 2, I will obtain approximately the same fit. And so the decision of the model will be approximately the same. That's why? Because the logit or the linear model are not unstable enough to give good result in bagging because, okay, they give approximately the same decision, even I change the sample used to estimate them. That's why you will never find bagging logit, bagging linear regression model. On the contrary, the trees are often used for the bagging. Why? Because if I change a little bit, the training sample, I will have a very different decision tree. And so with a small modification of the sample, I will have a very different decision tree here and here. And so the correlation will be small. That's why in general, we bag some trees, but for instance, we never bag we never bag linear regression model, but other models which are stable, so etc. are not bagged. Okay. Do you have any question about that? No? Yes, Ahmed.
So, theoretically speaking, would neural nets be something good to bag?
Sorry?
They are, I think, theoretically speaking, would neural
Yes.
nets be something good to bag, to use bagging on?
Yes, in general, because they are also sensible to a small variation of the training sample. Yes.
Okay. Of course, it's practically very hard, but
Yes.
theoretically.
But in general, it's not done. Okay, but theoretically, could be a weak learner that is sufficiently dependent.
Unstable?
Yes, unstable.
Okay, thank you.
Bagging comments. Okay, this is the same idea, so I don't. Okay, so okay. Tomorrow we will try with the bagging. So a bagging classifier. There is a bagging classifier method. Okay. So what are the options? Base estimator and estimator. I hope that you understand. So what is the base estimator? This is simply the type of algorithms that I want to bag. A decision tree, a logit, a SVM, whatever. And n estimator, what is n estimator? It is a number of bags. This is B, capital B in my notations. Then I have other options, which are max sample, bootstrap, etc. So max samples, number of samples to draw from X to train each base estimator. If by default, it is 1. If I put a float, this is a proportion. For instance, if I write as an option 0.3, it means that M is equal to 30% of the sample size N. So this option by default is equal to 1. It means that M is equal to N. I can put, if I put an integer, it means that M is equal to 10. So I fix the number of samples that I want to bootstrap. And if I indicate a float, then this is a proportion. It controls the proportion of that relates the bootstrap sample size to the initial sample size. Max feature. Okay, so I don't want to discuss this option because we will discuss this option within the random forest model. Bootstrap. You can put an option. Bootstrap is by default, it is true. And you can say, okay, none, okay, false. If I want to do a bagging, I have to let true, because if I don't never understood this option, because if I put bootstrap is equal false, then this is not a bagging. Because why? Because this is not a bootstrap methodology. And bagging is a contraction of bootstrap and aggregation. Okay. Bootstrap feature, I don't want to comment this option because, okay, it is related to the random forest. So let us say, this is very simple. This part of the code is related to the way to simulate some data. Okay, so it is not important. Let us imagine that I have some data. So I use from scikit-learn ensemble, ensemble for ensemble method. I import bagging classifier. I have also a function that is bagging regression. Okay, but if it is a classification problem, I use bagging classifier. What is the instruction of bagging classifier? Enfin, the way to proceed. Estimator equal the type of model that I want to bag. Here, this is a support vector machine. Okay, support vector machine, support vector classifier. This is an algorithm, but in general, we will use bagging decision tree. So I will change here to say classification decision tree. I will use 10 bootstrap samples and random state just to control, etc. And this is always the same type of instruction. At the end, I fit this back model on a sample X and Y. And here I have my bagged decision tree or bagged SVC estimate or train on this sample. Then using this model, I can make some prediction. I can compute the accuracy, etc., whatever, etc. This is always the same. But it's not possible for me to have a representation of this model. Why? Because this is the average of 10 different decision trees. I have just a link between X and the forecast. Give me the X, 0, 0, 0, 0. I will give you a forecast for this individual. Okay? This is why you have a black box, because at the end, you enter the X, you have a black box here, which is my bag, my bag model. Okay? And then I have the prediction. Okay. I propose to stop here, except if you have some question, naturally, obviously. Maybe just let me check something before to stop. Yes. If you want, I have a very short count. I think that you can do it in 5 minutes. Do you want to do it? It's not an obligation. It's okay? Okay, let's go. There is only 5 questions, okay? Okay, is there anyone want to join a Kahoot or not? Otherwise, I propose to start. It's okay. Okay, let's start. Ensemble methods. One of these methods is not an ensemble method. Great. Stacking is an ensemble method. It's just the idea to stack the model, keep each model at each stage. And okay. True or false? Bagging aggregates weak classifier trained on bootstrap samples. Great. This is exactly the definition of the bagging. This is the aggregation of weak classifier trained on bootstrap sample. Sorry. True or false? Bagging increases the variance of the hypothesis resulting from aggregation. False. Bagging is all the more effective when Great. Idea is to have bootstrap trees that are poorly correlated with each other. Maybe I have to change because if someone has chosen the green solution, bootstrap trees have lots of leaves. It could be related to the ideas that have a low bias and high variance. Okay, but okay, the idea is to use correlation. Okay. And true or false? The deeper the trees, the less bias bagging presents. Less bias there is. This is true. The deeper the trees, okay, the less bias bagging the bagged model has. Congratulations to Mireille. Yvka. And Nada. Well, Ahmed made an error at the end. I think that because he was a specialist of the bootstrap, but at the end there is maybe, but whatever. Okay, I think that you have understood the general idea of the bagging. So tomorrow we will continue with bagging in general. We just have to introduce what is the error out of bag, the out of bag error. And then we will discuss a variant of the bagging, which is a random forest. And then we will apply in practice with Colab and Python, a random forest to observe the advantages of this approach. And finally, if I have time, I will introduce you what is a boosting method. What are the boosting methods? So have a nice evening, except if you have some question, obviously.